Just about the delay. Okay, so I told you for spot speed and travel time studies, the calculations are similar. Okay, and we applied it in both cases. For control delay, there are specific equations which we haven't used earlier. So you will see them today, inshallah. Okay, the first thing which I explained to you last time that when you're talking about a highway, the delay can simply mean when you stopped. Okay, but when you're talking about an intersection, the delay includes more than the time when you stopped. So when you come to the intersection, your reaction is to slow down because you are coming towards the intersection, and then you may have to stop if there's a queue, the signal is red, and you don't have a chance to pass, and so on and so forth. So this stopping is also part of the delay, and then once you start moving, you will take some time to accelerate back to your normal speed. So all this is considered part of control delay. Okay, so intersection has a broader definition of delay, which is called as control delay. It includes three parts: deceleration, acceleration, and stoppage. Yeah, I believe there is sound. What about the others? Can they hear me? Okay. So how are you? There must be something with your system. Okay. So the term which they use for normal speed is called ambient speed. Okay. So this is where you want to reach, and the same definition applies to any type of intersection control device. It could be a signal, it could be stop control, it could be roundabout, and so on. Yes, go and come back. Yes. Okay, so how to measure control delay? We will discuss two procedures for control delay, one for signals, the other one for roundabouts. Okay, one for signal, the other one for roundabouts. Okay, if you have a stop sign or something like this, then there are other procedures for that. Okay, or you can adopt the procedure for the roundabout as well, but the more critical ones are for the signal and for the roundabout. The procedure is given in Highway Capacity Manual of 2000. It requires two observers at the same time for each direction, for each movement. Okay, so one of the observers, okay, before you start, so you decided what location, what movement you want to for what movement you want to calculate the delay. You arrange two observers for that movement. Now you have to select the time. So for the time, you have to meet two conditions. The first condition is that the queue length, when you are doing the survey, the average queue length. Okay, obviously at any particular second it can be more than this, but I'm talking about like most of the time. So you see that the queue is longer than 20-25 vehicles, and even when the signal becomes green, it becomes again the same length of the queue very quickly. Okay, or the queue is so long that even when the signal becomes green, even after the vehicles passing, the remaining queue is still very long. So this is not a good time for doing the control delay study. Okay, so they call them the undersaturated conditions. When the queue is smaller than this range given here, 20-25 vehicles. When the queue is smaller than these are called as undersaturated conditions. Another condition or another indication of undersaturated condition is having no overflow. Okay, that's the third point mentioned here, having no overflow. Overflow means what? When the signal becomes green, the vehicles which were already in the queue, all of them are supposed to move. All of them are supposed to clear the intersection. Supposed to. But you know, sometimes the queue is so long that one green is not enough to clear that queue. So this is called as overflow. Okay, so overflow is a condition where the queue needs more than one green time to get cleared. And by the time those vehicles clear, the new vehicles are already extending the queue. So this is another indication that the conditions are not undersaturated. So we want to do the observations in undersaturated conditions. The procedure is viable or is applicable for undersaturated conditions. Okay, the reason why we are focusing on undersaturated conditions, because in oversaturated conditions the delay is not because of the intersection. The delay is because the demand is very high. Okay, so we are not looking at that delay. For the intersections, I want to calculate how much is the delay because of the signal. Okay, not because there are too many vehicles. Okay, so this is why we call it the control delay. Okay, so that's why we are looking for undersaturated conditions. So we talked about the time, number of observers required, and another thing which you will require is the free flow speed. Now we know free flow speed is what is speed? Tell me, what is free flow speed? Tell me. What do we mean by free flow speed? FFS. Yes, can somebody tell me what is free flow speed? No one?
There is no traffic signal.
When there is no traffic signal, okay, or when there is no traffic signal, then there is no traffic as well. Okay, no signal and no traffic as well. So traffic has to be very low. So if you do it on no congestion. Okay, so if you are doing it without the signal, but the highway is already full, that will not be called as free flow speed. So free flow speed must be known. Now there are two ways to find out the free flow speed. Now remember, you are doing it for an approach of the highway. Okay, so for example, let's say I have so this is my intersection and I'm doing it for this approach. Okay, so this approach is coming from this highway, right? This highway. So I need the free flow speed of this highway. So how to get it? You may you can find out the free flow speed for this highway at some other location. So it's the same highway, but I will not do it at this location because this location has a signal. So people will not travel at free flow speed when they are approaching the signal, because they know that signal could be yellow or green or whatever, or they could be a queue. So I can do it at any other point on the same highway. So the free flow speed is considered valid for all points on the same highway until the design is same. Okay, so it doesn't matter whether you are doing it at the intersection or some other point. So the same speed which you did at, or you found at some other point, can be taken for the intersection. No problem with that. Okay, so this is one method of doing it. The other method, which is more time consuming, is that you take free flow speed, or so you are doing it at the intersection now. The other method is you take free flow speed at the intersection itself, but you only take the samples of vehicles which approach during green without queue. Okay, during green without queue. So you know, there are some lucky people, they come, the signal is already green and there's no queue as well from the previous red, so they are going at full speed. Obviously they don't want to stop, right? They have the golden chance to move. So you only take these samples. Okay, so now you can imagine how many of these samples you can find in 1 hour, let's say. So if you are doing at some other point, you can take all the speeds which you like, but here maybe 10 vehicles are passing and only 2 of them passed during green without queue. So you would only take 2, not 10. Okay, so these are the methods to find out the free flow speed. Okay, so these are the prerequisites. Okay, then we have two observers, right? So observer 1 is doing what? Observer 1 is taking count of the queues. So how many vehicles are in the queue? He is counting uh, uh, periodically. Okay, so after every few seconds you give him a time, that this is your time interval, and after this time interval you will count how many vehicles are in the queue. Okay, and this time interval is repetitive. So let's say if it is 10 seconds, so after every 10 seconds he will look at the approach and he will count the number of vehicles in the queue. This is his job, the main job. Okay, now you have to decide about the time interval. The time interval should be between 10 and 20 seconds. The time interval should be between 10 and 20 seconds. This is like from their experience. Okay, now how do I decide what number between 10 and 20? So what we do is you go and look at the cycle length of the signal. Cycle length means what? So signal goes from red to yellow to green to yellow, and then red starts again. So from the start of one red to the start of the next red, this is called as cycle length. Okay, so you start your stopwatch, signal has just become red, you start noting the time. Signal does red, green, yellow, red, yellow, green, yellow, and then it goes to red again. This is where you find out the cycle length. Okay, now what is the connection between the time interval and the cycle length? The cycle length should be a multiplicative of the time interval. Okay, or the term which they use is integral divisor. So if I divide the cycle length with my time interval, I should get an integer value. I should get a whole number. For example, cycle length is 60 seconds. Okay, so if I select the time interval for this observer 10 seconds, so 60 divided by 10 will give me 6. This is integral divisor. Okay, so 10 is allowed. Now let's say if I select 11 seconds, so 11 seconds is between the given interval 10 and 20. Okay, so this is between the range, but if I divide 60 seconds by 11, the 60 is the cycle length. If I divide it by 11 seconds, it will not give me an integer number, it will be 9 point something. Okay, so that means 11 cannot be taken here. Okay, and if you do 12, okay, if I divide 60 by 12, is it an integer or what? Tell me. Can I take 12 seconds as my time interval or not? Will it give me an integer? Yes. Okay, so this will give you like 5 or something. Okay, so this is this is how you decide about the time interval for this observer. Okay, then he has to count the number of vehicles which are in the queue. So we need to define what we mean by queue. Okay, so when the vehicles arrive at the intersection and they cannot move, okay, because there's already a vehicle in front of them, so that means they have joined a queue. So the vehicles which are moving towards the intersection, or they are stopped in front of the stop line, they are in the queue. Okay, either they are moving towards the intersection together, or they are stopped at the intersection, they are in the queue. The queue is for a straight movement. The end of the queue is the stop line. So when a car passes the stop line, it has gone from the queue if it is going straight. If you are doing it for turning movement, okay, then the end of the queue is the next side. So again, let's say I'm doing it here. If I'm doing it for this approach and this is my stop line, so when a car crosses this line, I will not count it in the queue. I'll only count the cars which are behind it. Okay. If I'm doing it for this approach, the left turning, okay, then the queue continues till this side. So this is the entry of the next road. Okay, so till the car is behind this line, I will count in the queue. Okay, so for a straight, I will start counting from here backwards, and for the turning, I will start counting from the entry of the next road to backwards. Okay, and this is obviously when they are moving. If they are stopped, then obviously you will look at the stop line for both of them. Okay, yeah. Now this guy, you will give him a time interval, not time interval after how many seconds he's going to do the queue count, the total time. Okay, so he will do it after every 10 seconds, for example, and he will finish in 10 minutes. Okay, so for throughout the 10 minutes, 10 seconds after every 10 seconds. Okay, so 10 the total time. Now the total time, when the total time finishes, he will look at the queue. Okay, when the total time finishes, this guy will look at the queue. Okay, he has to finish, he can finish at the end of your given time if the queue at that point of time is 0. Okay, so you gave him 10 minutes. Exactly after 10 minutes, he looked at the approach and there were no vehicles in the queue. This is done. He is done. He can leave. But let's say after 10 minutes, he looked at the road and there are 2 vehicles still in the queue. Okay, so now his time will extend until these 2 vehicles leave, because these 2 vehicles entered the intersection or entered the queue during his time. So if he doesn't finish them, if he doesn't finish till they are gone, then these 2 will not show in the calculations. Okay, so your calculation will have slightly more error. So 2 is just an example. It can be 10 vehicles as well, so the error will be higher. So the point is, so he was doing it after every 10 minutes or every 10 seconds count. He finished 10 minutes. Now there are 2 vehicles in the queue. He will wait for another 10 seconds. Okay, he will do another count for after 10 seconds. Now after 10 seconds, if these 2 vehicles have gone, so now let's say maybe there are 5 vehicles in the queue, but those 2 which he was looking at in the previous time interval, those 2 have gone. So now he can finish as well. So he will do this last count and he can finish. If those 2 have not gone, then he will continue. So maybe the signal is red for 30 seconds and he is doing the count after every 10 seconds. So it may take him 2 to 3 counts more before these vehicles are gone. Okay, so for observer 1, he is counting queues. You have to select a time for him. We have defined what we mean by queue and we have given him when he is supposed to finish. Then we have the second observer. The second observer is taking count with the first observer. So he is doing the he will stay till the same amount of time till the first observer is there, and he is counting 2 things. He is counting how many vehicles arrived and how many vehicles stopped. How many vehicles arrived, how many vehicles stopped. So when a vehicle comes, he will note it down, +1. If that vehicle stopped, +1 in the other column. Okay, if there will be some vehicles which will not stop. Okay, they will come during green and go without stopping. So that vehicle which comes during green and goes without stopping will not show in the second column. Okay, so this is for observer 2. Okay, once you have these observations, we have to perform a set of calculations to get the delay for the signal. I told you we have not used these equations earlier, so you will see some new equations here. This equation which you see here is called time in queue delay. Time in queue delay, TQ. So what do we need to calculate TQ? We need the interval you gave to the first observer for counting number of vehicles in the queue. The short interval, okay, the seconds interval, not the total time. The one which was integral divisor for the cycle length and blah blah blah. between 10 and 20 seconds. So that value is is. Now if he is doing it for 10 minutes and he is counting after every 10 seconds, so he will have many observations, right? Maybe, I don't know, 60 or some observations after 10 minutes. So if you sum those observations, all those observations are taken by observer 1, you get summation VIQ. So VIQ means each observation of observer 1, each count of Q for one time interval. Okay, and you add all of them, that will be summation VIQ. Then we have VT, which is total number of vehicles arrived during that time. Total number of vehicles arrived during that time. So that is coming from observer 2. So IS and VIQ is for observer 1 and VT is from observer 2. And then we have 0.9, which is the equation constant. Okay, then the next set of things you need to calculate is VSLC, vehicles stopped per lane per cycle. So vehicles stopped will be given by observer 1, sorry, observer 2, observer 2. Vehicles stopped is given by observer 2. Number of lanes, you will just count, go and count. Number of cycles, this is for which you did the study. Okay, so one cycle is red to red is one cycle. So how many times this happened during your study? How many times the signal went the whole cycle? So again, this is counting, you have to count. And I will show you in the table later on in the example that this is done during your study. You make the observation chart in such a way that the number of cycles are automatically counted. I will show you. So vehicles stopped per lane per cycle. Then we have fraction of vehicles stopped, which is number of vehicles stopped upon total number of vehicles. Both of these counts are coming from observer 2. How many vehicles stopped and how many vehicles came in total. Both numbers coming from observer 2. Once you have all these things, now we move on to the last item of this calculation, which is the control delay. Delay because of the signal. So you need TQ, time in Q, delay, calculated here, the first value. You need fraction of vehicles stopped, we calculated here, the last value. And you need correction factor. Correction factor has a table. Now remember I told you that you need the free flow speed as well. We haven't used free flow speed until now. So now you can see here in this table the free flow speed is being used. So we need VSLC, the second value here, okay, and we need the free flow speed. Based on the basis of that, you will have the correction factor. Okay, let us look at an example. Before the example is a chart, observation chart. So you see the details on the top, okay, where, when, who, so on and so forth. Number of lanes are already recorded, and the interval for observer 1 is given here, okay. Cycle length, you will note it down because you have to decide about the interval. And vehicle stopped and vehicle total, VT and V stop. This will come from observer 2 once the study is finished. Observer 2 will have his her or her own sheet where he is doing the counting. Once the counting is finished, he will come back to observer 1 and he will give him these numbers to write on this sheet. Okay, so you write the time here, you write the cycle number. Obviously the cycle from where you start is cycle number 1. Okay, now since your interval is integral divisor of cycle length, so in one cycle you will have multiple observations. Okay, so going back to the example, 60 seconds of cycle, 10 seconds of interval. So 60 divided by 10 means 6 observations. So in each cycle you will have 6 observations. So I'll fill up from column 1 to 6. Okay, and then I will go to the next row. It will be the start of the next cycle. Okay, so because I already know the cycle length, I already know the interval for observer 1. So I know how many observations I can have in one column. So after these observations, I go to the next row, and the next row means next cycle as well. Okay, and to make sure, you will write the time for each cycle here. Okay, now remember, each cycle means start of red, so you have time. The signal is red, so now you have time to actually write these numbers. Okay, so this is how it is designed. This is the real data. So you can see the clock time, cycle number. You can see the time given for observer 1. So you can see each value is after 20 seconds. Okay, so IS is 20 seconds here. The interval given to observer 1 is 20 seconds. And then in the first cycle, when the signal was red, he observed 4 vehicles in the queue. After 20 seconds, he observed 7. After 40 seconds, he observed 5. Then he went to the next cycle, right? 60 seconds done, right? 0 to 20 to 40. After 40, you will have 60. 60 means next cycle. Okay, and these are numbers for the next cycle. So if you add all these numbers, you get summation VIQ. Okay, summation of these values, the values which you observed in all the cycles. Then we have two values from the second observer, which he was counting. So he saw 120 vehicles coming and 75 stopping. Okay, and they measured somehow. I already told you two methods of measuring free flow speed. They used any of these methods and their free flow speed is 35 miles per hour. Before we move on to the calculations, I have a small question. We have 120 vehicles which came to the intersection on this approach. And the number of vehicles which were in the queue is 132. So 132, 120. How come number of vehicles in the queue are more than number of vehicles came to the intersection? How is this possible? Yes, how is this possible that you can have more vehicles in the queue than you had actually on the intersection? Anyone? Yes, you are right. Number of vehicles in the queue can be counted more than once. So a vehicle, so let's say these 4 vehicles, the first 4 vehicles, these ones, they were counted here. Okay, when he looked at the intersection after 20 seconds, these 4 vehicles are still there and 3 more are added. Okay, so this 7 is this 4 plus 3 more. Okay, so and the same thing may have happened here as well. So this 5 is part of this 7. Okay, so when he is counting number of vehicles in the queue, counting more than once is allowed. It is possible. Okay, so number of vehicles in the queue can be more than total number of vehicles. Okay, now let us move to the calculations. Okay, we have to find out the control delay. So the first thing we calculate is TQ. Okay, TQ was IS multiplied by sum of VIQ divided by VT to 0.9. Okay, IS is the time interval, which is 20 seconds. Summation VIQ is given, but it's the summation of these 3 columns, the counting columns, which is 132. And you need VT, so VT is 120. Okay, so what is TQ here? How much is TQ? 19.8, and the units are seconds per vehicle. Average delay per vehicle in seconds. The next thing we need to calculate is vehicles stopped per lane per cycle, which is how many vehicles stopped divided by number of lanes, number of cycles. Okay, how many vehicles stopped? We have 75 vehicles. Okay, how many cycles we have? You can see each row is a new cycle, so 10 cycles. how many lanes we have? It's given here. We have 2 lanes. Okay, so how much is VSRC? 3.75. Okay, so VSRC is 3.75 vehicles stopped per lane per cycle. Then we go and calculate fraction of vehicles stopped, which is vehicles stopped divided by total vehicles. Okay, so we know both of them. Total is 75, sorry, total is 120, stopped is 75. 75 by 120. How much is that? Okay, 0.625. Okay, now we can go for the final equation, which is for the control delay. Okay, so control delay was small d, the time in Q delay, okay, plus FVS into the correction factor. Okay, time in Q delay we already calculated 19.8. FVS, fraction of vehicles stopped, 0.625 into the correction factor. Correction factor needs this table. Okay, what is my free flow speed? 35. So this row here. What is my vehicle stopped per lane per cycle? 3 point something, right? So this value here from here. Okay, so 5. So how much is this? Okay, so and again the units are seconds per vehicle. So this signal causes 22.9 seconds per vehicle of delay. Okay, on average every vehicle is delayed by 22 seconds because of this signal. Okay, we have similar data. Okay, this one has only one lane. The data is given here. Total vehicles stopped. You have 15 cycles now, and you have the time interval of 15 seconds here. IS is 15 seconds. You can see it on the top. So from 0 to 15 to 30 to 45. Okay, and number of cycles is given here. Each row is a new cycle. Okay, so first of all, you will calculate. It's not given here in the last example. They already did the summation for you. The first thing you will do is do the summation of these things. Okay, so that will be your summation of VIQ. Okay, and then you will repeat the entire calculation which we have done, but the number of lanes in this case is 1. Okay, any problems, any questions? Okay, so I leave it up to you. You need to try it yourself. I move on to the next part, which is the delay for roundabouts. So I said I will do 2 of them, signals and roundabouts. Signals we already did. This is now roundabouts. Roundabout in terms of calculation or in terms of observation is quite simple. You need the volume in each lane of the roundabout, and you need the volume on the roundabout itself. Okay, so you can see it over here. You need this volume for each lane. If there are multiple lanes, 2 lanes, then you need to know for each one of them. And you need this volume. Okay, so you need these 2 volumes for doing the calculation. So it's a simple counting. You can do simple counting over here. So after you have counted these volumes, you can look at the equation, the large scary equation over here for the delay. This is again control delay, but in this equation we have other parameters. You can see C value here. C is the capacity of the lane. Okay, the lane which is entering the roundabout, capacity of the lane. Then you need, then you see a value here T, capital T. Capital T means the time interval taken for counting the flow, which is normally 15 minutes, but it should be converted to hours for this equation. So 15 minutes convert to 1 hour means 0.25. Okay, so you can consider it like a fixed value 0.25. Capital T is 0.25, but the logic behind is that you are taking it for the 15-minute interval. Then we have the x value here. You can see x coming up multiple times here. So x is a ratio of V over C. Okay, C is the capacity and V is the volume of the lane. Okay, C is the capacity of the lane, V is the volume of the lane. So volume you need to count. I already mentioned you have to find these volumes, and C is the capacity which you need to calculate. Now how to calculate C? I'm using C here for X, and I'm using C separately as well. So I need the capacity. So there are some equations to calculate C. Before we move on to that, just pay attention here. This part, it says 5 multiplied by minimum of x or 1. Okay, so if x was 0.3, then you will multiply 5 with x 0.3. If x was 1.5, then you will multiply 5 with 1, not 1.5, because you have to take minimum. Okay, so this is what it means. Now going back to the question of from where do we get the capacity of the lane. Okay, now this depends upon how many lanes you have on the roundabout and how many lanes you have on the road itself. So you can see roundabout with 1 lane or 2 lanes, and you can see lanes with 1 lane and 2 lanes as well, a road with 1 lane and 2 lanes as well. Now we are calculating the capacity of the lane on the road, not the lane on the roundabout. Okay, these equations will give you the capacity of the lane on the road. So when I have 2 lanes, I see 2 equations. Okay, when I have 2 lanes, I see 2 equations because each one for the each lane of the road. But if I have 2 lane roundabout here and 1 lane only, I see only 1 equation. Okay, this is because we are not talking about the lane of the roundabout, we are talking about the lane of the road. Okay, in all these equations you see the same term is used, which is VC. Okay, and hopefully you will not ask me what is E. Yeah? I hope you should know that. But VC is this volume, the volume on the roundabout. Okay, this one. Okay, so in all the equations you need the volume of the roundabout. Okay, and CR means capacity of the right hand side lane, CL means capacity of the left hand side lane. Okay, now you got a C value from one of these equations from the first table, but on this roundabout there is some pedestrian crossing as well. So you have to look into the second, and you have the number of pedestrians. Okay, so you have pedestrian crossing and the number of pedestrians are given to you, how many pedestrians are crossing from this side in 1 hour. Then the capacity you got from the first table must be multiplied with the adjustment factor for pedestrian crossing. The second table gives you the adjustment factor. Again, it depends upon how many lanes on the road you have. Okay, and how much crossing volume you have, and how much pedestrian volume you have. So for example, the volume crossing volume you have on the roundabout, so remember VC is on the roundabout, right? So the crossing volume you have is 1000, and you have single lane road, so you are here, so your factor is 1. So you'll take the capacity from here, multiply by 1. Okay, let's say you have single lane road, but your roundabout volume is 500. So you're not here, you are here, and you have 50 pedestrians crossing. So you are here. So then you will calculate the factor for pedestrian from this equation and then multiply the with the capacity from the first table. Okay, so the point is you have to look at how many lanes you have, how much volume you have on the roundabout, and how much volume of the pedestrians you have. Once you do that, you will know which factor will apply. You will calculate that factor from the second table and multiply with the C value you got from the first table. Okay, so this is how the capacity is calculated. This is an example to clear out this process. Circulating volume, VC, okay, volume of the roundabout. We call it VC or circulating volume. And it's a single lane roundabout. And it has 100 pedestrians crossing. Okay, so what will be the capacity if the road is also one lane? Single lane roundabout, single lane road, 100 pedestrians crossing, and 650 is the volume on the roundabout itself, circulating volume. First thing is I will go to the first table and look for which equation applies to my case. One lane roundabout, one lane entry. So I'm going to apply this equation, the first one. Okay, so if VC is 650, and how much is my capacity? Tell me. If VC is 650, how much is the capacity? Okay, sure. Is anyone else getting the same value? So it's 1130, okay? This is comma, this is not a point. And this is minus 0.001 into 650. Okay. Moving on, now we need to look at did they give us pedestrian volume? Yes. So that means I can go to the second table. I have single lane road, so I will use one of these three. My volume is 650, so not here, it's here. My pedestrian volume or here or here. Now pedestrian volume is 100. So 100 means I'm here. Okay. So 650, 100. I'll calculate the factor using this equation. So if n pedestrian is 100, how much is the factor? Tell me. Okay, so the final capacity will be 590 multiplied by 0.9863. Okay, and this is in vehicles per hour. Okay, so this will be the final capacity which you will use in this equation. Okay, your C and X value will be calculated using 582 after the adjustment factor, not with the adjustment factor. Okay, so moving on. Now this is another question where we are going to calculate the delay itself. So we have two lane road now. You can see it over here. Single lane roundabout. The conflicting volume, circulating volume 600, and the volume for each lane is given there. Okay, we have to find out the delay for each of the lanes. Because we have two lanes, we can have two values of delay, one for left hand side lane, one for the right hand side lane, because each one has a different volume. Okay, we'll start with the calculation of capacity first. Okay, if I go there, I remember my circulating volume is 600, VC is 600. Okay, so single lane roundabout, two-lane road. So I'm here, and you can see both equations are same. That means if you have a single lane roundabout, then capacity of both lanes of the road is same. Okay, so tell me now, what is the capacity here for both the lanes? It's the same equation. So VC is 600. Okay, 620. Okay, good enough. Almost 620. Okay, moving on. So if my capacity is 600, then I need to calculate x for both the lanes because I need to use x. So x for the right hand side lane. Now remember, capacity is same, but the volume in each lane is different. 600 and 400. Left is 600, right is 400. So x will be different. So for right it was 400, and for left it will be 600 divided by 620. So how much are these values? Okay. Okay, good. So now moving on to this big equation. Now I have everything which I need. Now I can use the same equation with different x values. So only the x values will change. Okay, T is 0.25 is given here. C is 620. In this case, both lanes have the same. So, but the x, when you're doing it for the right hand side, the x is 0.6 something, and when you're doing it for the left hand side, the x is 0.9 something. So, what will be the delay for each case in this example? So, T is 0.25, C is 620, and x is what you have in your comments there. Yes. XL is 0.968. You can see the one which is given by Mariam. I believe the value is correct. Okay, this is for the right hand side, and for the left hand side, how much? Okay, 18.9, both of you, good. $54.7. Okay, now if you, a small point here, the values are correct, well done. A small point here, if you look at the volumes, these are the volumes, right? 600, 400. So how much is the change in the volume? 200 vehicles. Okay, and how much is the change in the delay? 3 times. 18 plus 18 plus 18 is 54. Okay, so a small change in volume can, so it's not linear. Okay, they are directly proportional. If you increase volume, delay will increase, but it's not linear. So it's not like I will increase one vehicle and the delay will increase by 1 second and it will keep on doing this. No. So it's non-linear. So that's why we need to be careful about design of these things. Okay, this is another example for your practice. A one lane roundabout and one lane of the road. Okay, so it's simpler. You only have to calculate it one time. Okay, capacity is one time, the x is one time, and so on and so forth. Okay, uh, so it's the same question but only done once. Still, there is no volume for the pedestrian, so you will not apply the adjustment factor like we did in the last example. Any problems? Anybody has any problem? Okay, so then I can move on. You will see at the end of the slide some other questions. These are again from the book, both the books. You can use them for more practice. Okay, moving on to the next topic, which is volume studies, and this is chapter 10 of the book, and we are covering the same silo, which is the ability to collect and analyze traffic data. We already know about some of these parameters. Okay, so volume can be daily volume, hourly volume. We have rate of flow, which is flow converted to per hour rate. We have demand, which is number of vehicles trying to enter the highway, and we have capacity. You just calculate capacity for the last examples as well, which is the maximum flow rate the highway can handle. Okay, so we already know about these four parameters, and all of them can be in vehicles per hour, and later on we will see them in passenger cars per hour as well. So PC means passenger cars per hour. So the main point here is the volume. So we are doing the volume studies. Now volume, so if I look here, so I have volume and then three other things, right? So volume depends upon which one of them. Does it depend upon rate of flow or demand or capacity? Volume depends upon which one of these factors. So you have volume and then you have the other three. So which of the other three affects volume? Just take a guess. Is volume affected by capacity? Is it affected by rate of flow? Is it affected by demand? Yes, anyone? Flow? No. Volume is affected by the demand. Okay, volume is mainly affected by the demand, and the other things are also affected by demand. So demand basically you know affects everything else. So what makes that, so demand makes everything change, and what makes the demand change? The demand changes because of us, because of the travelers. So because of the travelers, the demand may change in different times of the day. So you have times when the demand is higher, people are going to school, offices, and so on. and you have off peak hours where demand is nothing. Demand changes according to the day of the week. So you have people going to, again, offices and other places, workplaces, study places on weekdays, and on weekends they go to some other places, okay, for entertainment, for shopping, and so on. And then demand can change according to month and season as well. So the demand may be higher towards a beach during summer months. The demand may be higher towards an enclosed facility in winter months, and so on and so forth. And the demand could be because there's an event, and this event can be planned, or it can be something natural, something which suddenly happened. Okay, for example, the situation we have now, nobody planned for that. Okay, and Formula One, National Day, Eid, all of these are different events. Okay, heavy rain, we are having heavy rain tomorrow. So all of these are different events, and these events also affect demand. So uh, the demand is affected by a lot of factors. So demand is affecting everything, but the demand itself is not something which is fixed. So I cannot say on this day, on this time, the demand will be this much. So if I cannot say this, then that means I have problems in calculating the other things as well. I cannot calculate my capacity and rate of flow and volume properly because the demand keeps on changing. So in the modern times, they have gone towards a new technology, new approach, which is called as intelligent transportation system. And things have even moved farther from that as well. Now the new term which they use is not in the slides, but I will tell you. It's called as smart mobility or smart transportation. Okay, so ITS is a part of smart mobility or smart transportation. But the meaning of ITS is that to get real-time information about traffic, a system which gives you real-time information about traffic, and you can manage it on real-time basis as well. So you can change signal timing, you can change the lane assignment. Okay, how many lanes were straight, how many lanes were left and right, and you can change the speed limit on real time. Okay, traffic is this much here, let me give message to the drivers that they should not go in on this road. Okay, or I need more lanes for straight, let me have some electronic boards which says now we have 3 lanes for straight, and so on and so forth. So this is the entire concept of ITS, to get data and manage traffic in real time, to get data off and manage traffic in real time. And much of the ITS and smart mobility approach depends upon driver awareness. Okay, so I told you demand comes from us people. So you let the people decide, you inform them better so they can decide better. Okay, so the demand because of events or somebody is new, so you inform them that if you go from here you will be stuck in a traffic jam, and then they decide what to do and when to do and so on and so forth. So this is the whole idea or the main idea, but that doesn't mean the government will not do anything. Obviously if they see traffic jam, if they see a problem, they have to act, but at the same time they are also informing the driver, so it will reduce the load from the traffic authorities. These graphs show you the variation in volume in different times and days and so on and so forth. So the first graph, or in these graphs you see 3 different lines, each line belongs to a different day. Okay, and you can see the one of the day is Saturday and the other one is Sunday. Both of them are supposed to be weekends because the diagram is for US. So both of them are supposed to be weekends, but even you can see within the weekend it's not the same trend. Okay, so if we have for our case Friday and Saturday, so the Friday demand is not even the same as Saturday, although both of them are weekends. Because one is the start of the weekend, the other one is the end of the weekend. So it doesn't go the same way. And you can see the difference between different days, and you can see the difference between different types of highways as well. The 3 different charts are for 3 different types of highways. Okay, so you can see the each chart is different from the other chart. So each day is different from the other day, and each highway is different from the other highway. Okay, and even you can see the difference in terms of time on the same highway on the same day. So if I follow this curve over here, this one, so it starts from 1000 or something, goes up to 8000, a big change in the same day on the same highway. Okay, so this is how much variation we are dealing with. So it's not a small variation that's going like 100 vehicles plus or minus, then it's no problem, I can deal with it. But the variation is very large, so you have to be careful in recording the volume and using it and so on and so forth. Up till now, we have already talked about counting volumes on highways. We have done a trial version before we had this situation. And counting volume seems very simple because you are just counting. Okay, the car goes in front of you, you just count it. You count it using a device, you can count it on paper, okay, and so on and so forth. So now we will take it a step further and we will talk about counting which is done on intersections. So we call them turning movement counts, TMCs. Okay, so what is the turning movement count? The one which is done on intersections. On intersections, we prefer manual counting because of the turning movements. If you use a device, there's a chance that the device may just count the vehicle because it passed in front of the device or it moved over the device. But that car may have gone in any direction after passing from the device. So manual counting becomes more accurate in terms of the direction. But we know manual counting has other errors. So now people are using videos and cameras which can be processed directly. So you can count vehicles directly processed from the video. We have algorithms available for that. Okay, and some of them I believe are already like they're available. Okay, and like we said for the delay count, the volume count is also done from the time when from the point when the car departs the intersection. Departing means the stop line basically for straight, and when it gets to the other side for turning. The same thing which I explained to you for the delay count, for the delay observation. Okay, so a vehicle is considered inside the intersection if it is behind the stop line. Then if it is going straight, crossing the stop line means it has passed. And if it is turning, then reaching the other side means it has passed. Okay, so same rule which we have seen for the delay. For intersection volume counts, TMCs, we need to manage the number of observers. Okay, because intersection has many movements. If we have a four leg intersection, if we have something like this, okay, then each side can have this one, this one, this one. Okay, so each side will have three at least, and you can even count the U-turn as well. So U-turn means that there will be four. Okay, four on each side. Then 4 into 4 is 16. So you have 16 movements. So can I deploy 16 people at one intersection? I may have other intersections as well. So how many people can I deploy? I may have limited people in my organization. So you need to manage the number of people, but at the same time, you have to get the count properly as well. So there are some guidelines given here. So for example, if you have inexperienced observer, so some of these movements will be heavy and some of these movements will be light, meaning some of these will have more vehicles and some of them will have less vehicles. So you have to first of all see which ones are heavy and which ones are light. For light movements, inexperienced observers can easily do it, even if you give them more than one movement, because there are very few vehicles which are coming for that movement. For example, U-turn. Let's say there are very few vehicles which are taking the U-turn. So most of the time this person will be free who is counting the U-turn. So you can give him one more movement. Okay, so this person can do two movements. But if it is one heavy movement, the one which is continuously having vehicles, then you just assign one inexperienced observer to this movement only. Okay, but if he is an experienced observer, he is doing it for many years, He may handle two heavy movements as well. There are people who can do that, but you need a lot of practice and you have to trust that guy. That's just anybody can have a bad day, right? So I'm very good at my job. I'm very experienced, but today I have a headache. Today I have fever, whatever. So you need to be careful in assigning the movements. Okay, the heavy ones and the light ones. Light ones are no problem, but heavy ones need some consideration. Okay, if you have multiple lanes for the same movement, you may assign observers which are doing lane wise counting. We saw this in lecture 2 slides. Okay, so one observer is doing one lane at a time. So this is a good method because one lane means people will go one by one. So I will have less errors in my counting. If I give you two lanes and both of them are going the same approach, you will have simultaneous vehicles passing you, and then there are more chances that you will make a mistake. Okay, manual observations we discussed again in lecture 2 slides. Manual counting needs breaks as well, and these breaks can be alternative or within the counting period, and we have discussed both of them, we have seen both of them, we analyzed both of them in lecture 2 slides, so you can go ahead and have a look at that. Okay, so I will not go in details of that. So we need this so the observer is feeling fresh every time, and he has no problem of the pen and the paper and whatever. Okay. Okay, one thing which is mentioned here I forgot to say is the position of the observer, because movements are happening in different directions. So the observer must be positioned properly to see the movement which he is or she is assigned. So if somebody is taking this U-turn count and you put this observer over here, so from here is very difficult for him to see this movement. He's on the opposite side. He will have vehicles crossing him. He cannot see it properly, or she cannot see it properly. So the placement of the observer is very crucial here. Okay. Another thing is on intersections. What I mentioned earlier is we are counting departure volume, vehicles when they depart the intersection, meaning crossing the stop line or reaching the other side. This is the normal pattern. This is easy to manage even manually, because you are just looking at vehicles when they cross a certain point. Okay, but there are cases in which the departing vehicles are of no interest to us. This happens when we have oversaturated condition, or what they call as queue buildup case. Okay, so the queue buildup case is what? That the capacity of the intersection is less than the demand. The capacity of the intersection is less than the demand. So what will happen over time? The queue will keep on increasing and increasing, because the intersection is passing less vehicles and more vehicles are coming. So this is called as queue buildup case. So if you are in queue buildup case, then the vehicles coming are the actual vehicles you want to count. The vehicles leaving are the ones which are going from the queue. Okay, but I want to know the actual demand. The actual demand is in the queue itself. The actual demand is not passing completely from the intersection, so it's just getting stuck in the queue. So in those cases, I need the vehicles arrived, not vehicles departed. So first of all, I need to see if they're the queue buildup case or not. So how do I know queue buildup or not? There are two conditions given. One for signalized intersection, the other one for unsignalized. Unsignalized include roundabout, stop sign, whatever. Okay. For the signalized intersection, it has the same condition which I give you for delay, which is the overflow condition. Vehicles come to the intersection during red, signal becomes green. The queue is so long it doesn't clear in this green. So vehicles stop for more than one red. This is overflow condition. We discussed the same for in the case of delay as well. So this is indication of queue buildup. Okay, so on a signal, you just look at couple of times the signal becomes red, and every time it becomes red, do I have a new queue or the old queue is continuing? If the old queue is continuing, that means you have queue built up, you should look for arrival volume. Signal is not passing all the demand. If it is non-signalized, then obviously you don't have green and yellow and so on. So in that case, you will just look at the length of the queue for some time. Okay, and if you see the general trend is increasing, then you have the idea that it is queue build up. The general trend. Okay, you may count it, but obviously the count will increase and decrease. Okay, so you may do like, okay, I will count now 3 vehicles, let me come back after 2 minutes, let me see again. So every time you come and you see the count is generally increasing, okay, so maybe 8 out of 10 times it was increasing, that means queue build up case. And this is an indication you should go for arrival volume. So this is for the condition where you have the arrival, you need the arrival volume, okay, the queue build up case. Okay, I'll stop here. I will